Here we are doing thermoelectric devices for wearable electronics by Emily Roberts, Tristan Parks, and Jeremiah Long. Here is the overview of the presentation. We will be going over the introduction section, which includes what is a thermoelectric device, thermoelectric devices in real life, and the history of thermoelectricity. Then we will go over the characteristics of how they work, what are their properties, and the common materials used in thermoelectric devices. The applications that are mentioned in the presentation will be the thermoelectric generator and cooler and thermocouple. In conclusion, we will talk about the potential future of these type of devices and do a brief review at the end. A thermoelectric device is a device that creates a voltage in between two materials that have different temperatures at their junctions. The thermoelectric effect is the direct conversion of temperature differences to electric power, and which can also be reversed when power is added. When temperature differences are converted directly into electricity, this is called the Seebeck effect, which will be further discussed later on. Heating one end of a thermoelectric material causes the electrons to move away from the hot end and toward the cold end. When the electrons go from the hot side to the cold side, this causes an electrical current. The larger the temperature difference, the more the electrical current is produced, and therefore more power is generated. Here we are going to talk about thermoelectric devices in real life. One example is the Seiko's thermic watch that generates its power by harnessing the difference between the wearer's body temperature and the air temperature surrounding it. When wearing the watch, the user's skin is in contact with the rear case back surface, and the case top surface is exposed to the air. To generate power, the watch employs a thermoelectric effect known as the Seebeck effect. This occurs when the ends of two different metals are exposed to two different temperatures, creating a potential difference. To harness this effect, Seiko created a module composed of 104 or 52 pairs of semiconductors utilizing P-type and N-type elements. To produce the semiconductor elements, a bismuth and tellurium-based center material was used. This material has a good performance at room temperature with a Seebeck coefficient of 200 microvolts per K for both P-type and N-type elements. The general layout of the module can be seen here. The thermoelectric semiconductor elements are connected in series and placed between two substrates made from silicon, the material used in IC manufacture. The elements are extremely small at around 100 micrometers in thickness and 600 micrometers high. The complete thermoelectric generation module is 2.36 times 2.14 millimeters in size. The main purpose of this watch is to tell the time, have a perpetual calendar, and a power saving mode. The next device is still in progress, but is given the name of Flexible Tech. The main purpose of this device is to work as a health monitor. It would measure heart rate, blood oxygen, glucose, and other health parameters. The goal of the researchers is to create a flexible but not rigid device that is ergonomic and comfortable for the user. However, as of now, the flexible device is behind in performance and efficiency of its counterpart, which is the rigid device. The semiconductor elements in this device are connected electrically in series using liquid metal interconnects made of a non-toxic alloy of gallium and indium. The alloy provides a metal-like electrical conductivity and stretchability. The entire device is then embedded in a stretchable silicone elastomer. The silicone helps to increase the thermal conductivity to around 6 times greater. The researchers say that the technology in this flexible device has the same semiconductor elements, and therefore they need to only improve the efficiency of the device instead of trying to create something new altogether. In the year 1821, Thomas Seebeck found a circuit that could deflect a compass. The circuit was made of two different metals that had junctions at different temperatures. He initially believed that this was due to magnetism induced by the temperature difference and thought that the Earth's magnetic field was involved. After further testing, it was realized that a force, thermoelectric, was inducing an electrical current which by Ampere's law deflects the magnet. Seebeck figured out that the difference between the temperature between the two junctions produced an electrical potential voltage, which can force an electrical current in a closed circuit. The voltage produced is proportional to the difference in the temperature of the junctions. The constant, which is derived as an S or A, is known as the Seebeck coefficient and thermal power as T. In 1851, Gustav Mangus discovered that the Seebeck coefficient does not depend on the distribution of temperature along the metals between the two junctions. This shows that the thermal power is a thermodynamic state function. A thermodynamic state function includes several variables and depends only on the equilibrium of the system, much like a crystal. This is the beginning of the electrical device called the thermocouple. The thermocouple is used to measure temperature and will be discussed later on. A part-time physicist and full-time watchmaker, Gene Pelter, found that an electrical current would produce heating or cooling at the junction of the two different metals. He later showed that depending on the direction of the current flow, heat could be either removed from a junction to turn water into ice, or reversing the current, heat can be added to melt the ice. The heat created or absorbed at the junction is proportional to the electrical current. The constant is known as the Pelter effect.
We will now move on to how these devices work. Metals are good conductors because electrons can move freely within them, similar to a fluid in a pipe. Imagine you have a pipe full of water and you raise one end. The water will flow down the pipe from the high end to the low end. This is due to the water wanting to flow from high potential energy to low potential energy. In a thermoelectric material, the same thing happens to the fluid-like electrons when you heat it. Thermoelectric power results primarily from two physical effects, the Seebeck effect and the Peltier effect. The magnitude of the Seebeck coefficient varies with material and temperature of operation. The Seebeck coefficient is thus defined as S equals the negative change in V over the change in T. In this equation, change in V is the voltage difference between the hot and cold sides, and the change in T is the temperature difference between the hot and cold sides. The negative sign comes from the negative charge of the electron and the conventions of current flow. A negative Seebeck coefficient results in electrons being the dominant charge carriers, whereas holes are the dominant carrier in materials with a positive Seebeck coefficient. The majority charge carriers are said to move away from the heated side toward the cooler side. Minority charge carriers move in the opposite direction, but at a slower rate. Peltier had discovered that whenever a circuit of two dissimilar materials passes current, heat is absorbed at one end of the junction and released at the other. This is a linearly dependent and thermodynamically reversible process. However, applying a temperature differential, the reverse process occurs. The current is caused to flow, thereby generating power. The figure below shows a thermoelectric device in both cooling and power generation configurations. Shown is a thermoelectric cooler and a power generator. The current flow is labeled in the direction of the electrons. The efficiency by which a material is capable of generating power is governed by the figure of merit. As seen in the equation below, the figure of merit is most dependent on the Seebeck coefficient of the material. In the equation, the figure of merit is defined in terms of the Seebeck coefficient, the electrical conductivity, and the thermal conductivity. Maximum power generation requires the minimization of the thermal conductivity while maximizing the Seebeck coefficient and electrical conductivity. There are three fundamentally important properties of a thermoelectric system that must be optimized in order to produce a neo-ideal system. Unfortunately, these three properties are closely related and are usually inherent properties of a material. An ideal thermoelectric material will have a high electrical conductivity to minimize Joule heating, a high thermal power to maximize voltage generated per degree of temperature gradient, and a low thermal conductivity in order to maintain a high temperature gradient between the sides of different temperature. Thermal conductivity measurements on thermoelectric materials can easily be made using hot disk TPS instruments. These three properties can be used to calculate figure of merit, which is an overall indicator of the quality of a thermoelectric material in the equation shown. where S is thermal power over Seebeck coefficient, sigma is electrical conductivity, T is absolute temperature, and K is thermal conductivity. There is a variety of systems that are being investigated for their use as thermoelectric materials, and some of the more common ones include bismuth telluride, antimony telluride, and calcium manganese oxide. These systems have been investigated in some cases for many decades now. The most effective thermoelectric materials being produced today involve metal alloys or doped systems in which the electrical and thermal properties are altered through the dopant. To this day, most common thermoelectric materials are produced by heavily doping semiconductors to produce a N-type or P-type material based on the manufacturer's specifications. The doping of these materials typically produces a Seebeck coefficient of around 150 to 250 microvolts per Kelvin. Below are some advanced microscopy images of the surfaces of two different thermoelectric materials, shown here. To equip modern wearable technologies with thermoelectric-based devices, advanced methods were needed to produce materials that are strong but flexible. This is typically achieved by setting very thin layers of less brittle materials, such as bismuth telluride, and then weaving the circuits to be embedded within an organic polymer-based material that would protect but not disrupt the thermoelectric circuit.
Thermoelectric generators. Thermoelectric generators, or TEGs for short, operate by using a difference in heat flow to form a circuit that can be used as a DC power source. Electrons flow from the heat-applied surface to the colder electronic surface, creating an electronic field in the process. And the power of this electronic field is based solely on the difference in temperature between the hot side and the cold side. Wearable device examples include a thermic watch that uses body temperature to start the circuit, which then can be used to charge or continuously run the connected components. Thermocouples are voltage reading sensors that use an instrument to measure the electric field produced by the Seebeck effect that occurs only when electrons move from a warmer metal plate to a colder one, and the greater the difference in the temperature has a greater effect on the voltage read by the sensor. Thermoelectric coolers are possible due to the Peltier effect. A DC voltage is applied across joined conductors to create an electric current. As current flows, heat is removed at one junction and cooling occurs. Heat is then deposited at the other junction. The voltage can be reversed, and the effect can be reversed as well to have heating or freezing on either side. One wearable example is a prototype military desert-grade vest that cools the body temperature of soldiers in violently harsh conditions. Future works. Thermal energy is one of the largest sources of lost energy. A single person alone emits approximately 8.37 megajoules per day of energy. Over the course of a year, that number expands into the gigajoule range, and with a population encroaching up to 7.5 billion people, you can see how this wasted energy begins to add up. Proposed future technology has devised wearable TE materials to be vital in producing our own renewable energy, and also as a way of vastly reducing our global non-renewable energy footprint in the long run. Conclusion. Thermoelectric materials are being researched and developed constantly to improve the flexibility and effectiveness of the devices created using this renewable source, that is thermal energy. Generators and coolers that run off thermal energy are powered by temperature-dependent voltages caused by the Seebeck effect and Peltier effect respectively. Wearable thermoelectric-based devices will allow for users to power, heat and cool, or even charge objects solely from the body heat every person emits naturally.